sharing. This meeting's being recorded. Great. All right. So let me just get the, so I'll try my best to monitor the chat box, but I don't think I will really get to the, I don't know if I will be able to get to the questions in the chat box during the talk. So as Anna mentioned, the title of my talk is The Motion Fluids Underground, and the subtitle is How They Shape Our Natural and Engineered Environments. And so this diagram here, this cartoon here, I drew it actually 2 years ago in an effort to summarize all the kind of projects I've been working on. And thanks to the Miller Fellowship, which gives me all the freedom. And so I want to quickly give you, some idea of what these are. So I've looked at the fluid mechanics of carbon capture and storage, and specifically asked the question of what happens if we inject carbon dioxide underground and store it, and would it be a safe practice? And I've also looked into methane emissions in the ocean environment, and I asked the question of how much methane is coming out of the seafloor every year through these natural occurring methane venting processes. And with my current host, Michael, we're looking at how lava flows on land, and particularly I'm curious about how is lava able to travel such long distances on planetary surfaces. And largely, I've also delved into questions related to water resource and hydrology, and that's actually going to be the focus of my talk today. But before I get into the story on water, I want to quickly give you the reason why I study these systems. So when I go into these projects, the goal for me is to come up with predictive models that can inform us about how the subsurface environment evolve over time under these systems, and what are the best practices to manage our resources and hazards. And of course, even though the cartoons look really nice and simple here, the real world is very complicated, and there's almost impossible to make models that can capture everything. And therefore, by definition, all models are wrong. But I believe that some models can still be useful, and specifically, I think models that honor the important physics that capture the key mechanisms that are at play will be useful in predictions. And so today I want to focus on just one story, which is related to how water travels underground. In particular, I start by asking a rather simple question, which is how does rainfall recharge our groundwater supply in drylands? So I will define what is drylands in a little bit, but I want to just quickly introduce some of the key concepts in the story using this simple diagram here. And so first, precipitation is the amount of water that that trickles down onto the subsurface environment, and that includes generally rainfall and snowfall as well in regions that does snow. And a lot of that water, a big part of it will likely be lost back into the atmosphere through a process what we call evapotranspiration. So that's essentially evaporation and plant transpiration, the water uptake by vegetations. So evapotranspiration is a process that occurs predominantly in the topsoil, so the shallow parts of the subsurface environment. So then whatever is left, right, between after evapotranspiration will be eventually flowing down towards the deeper part of the subsurface and recharge our aquifer, which is where the groundwater is stored. And so these three key concepts alludes to a very simple relationship, which is the amount of groundwater recharge we expect would be equal to precipitation minus evapotranspiration. So however, even though this is a very simple equation, to actually do this calculation on Earth is very, very challenging. So for precipitation, it's actually pretty straightforward. We could directly measure how much rain we're getting or snow we're getting using, field gauges. The challenge really comes to the fact that it's difficult to measure or even model evapotranspiration. And part of the challenge comes from the fact that how much water that's being evaporated or transpired depends on the availability and the spatial distribution of water in the soil. And that itself is a complicated process. And so oftentimes we don't actually talk about evapotranspiration, but we refer to what we call potential evapotranspiration. So that is the total amount of evapotranspiration from soil when water is sufficiently being supplied all the time. So that is essentially the maximum possible evapotranspiration. Okay, so with all these definitions in hand, I can start defining what we mean by drylands. So drylands are simply places in the world where the potential evapotranspiration is larger than precipitation. So if you reflect this definition onto this phase space where you plot evaporation versus precipitation, right? Drylands is simply the shaded area above this green straight line of slope equal to 1. And you may wonder where California falls in this diagram. So that's where California is. So we are well into the dryland climate. And so California is not alone. Of course, there actually a significant portion of the world is considered as drylands. And so here's a map showing where they are. So drylands are really interesting because by definition, it is places where more water is being lost than being precipitated down. So according to this simple equation, we would expect no groundwater recharge in these areas. So in the worst case scenario, we do not expect recharge. However, there actually has been lots of evidence suggests that the reality for drylands are always better than the worst case scenario. So some of the indirect evidence include the fact that we have the presence of deep-rooted plants, such as shrubs and trees in these ecosystems. And these plants likely access water through the deep aquifers, which somehow is getting replenished. And directly, we can also actually measure the amount of recharge by measuring the water table underground. And there actually has been recent work that really shows the active recharge in the last 30 years in these very dry areas. So to refine the question I asked in the beginning, the new question I ask now is, how is it that in these dry areas of the world, how is rainfall able to bypass the evaporation zone to recharge our groundwater? So to answer that question, we'll go back to this simple diagram again. And specifically, I want to focus the rest of the talk about the process of water infiltration through dry soil. And so the reason we focus on this process is because the rate of water infiltration essentially determines how much water is available for evapotranspiration. And in other words, if water is able to infiltrate quickly, there should be less evapotranspiration. So the standard infiltration model in hydrology is what we call the Richards equation. It's proposed by Lorenzo Richards in 1931. So it's a nonlinear PDE that describes the evolution of water moisture, so water saturation in soil over space and time. And so here is a simulation in 2D of what this equation is able to describe. So we have a soil column that's initially dry, it's about 2 meters tall, and there's water coming down from the top at different rate. And so the blue emulates the water saturation. So one thing that this model is really good at is capturing the key observation that the wetter the soil, the easier water flows in the systems. But in the context of infiltration, what this model really suggests is that the rate of infiltration of water in the subsurface is solely determined by the rate of rainfall that arrives at the surface. So however, if you actually, this equation actually has been quite, even though it's a standard model, it's been controversial in the field because it's pretty much wrong about a lot of other things, even though it's good at capturing some of the key observations. So one of the things that the Richards model is not able to capture is when you direct to visualize infiltration in soil, you see a very different picture. So here's an analog experiment in the lab where instead of having soil, we have glass beads that are transparent. And the water is dyed blue, so you can see it. And the water will trickle down through a syringe, right, emulating rainfall. So I want you to just like think for a second, what would happen when water starts trickling down? Since now you have seen the Richards equation simulation. So far so good. The water is entering and it's percolating downwards. But then you're going to start seeing that at the infiltration front, you have these bumps start forming. And these bumps essentially elongate and turns into these, what we call gravity fingers. And they're essentially these water conduits that is very good at conducing water flow. And so if you traverse the infiltration front, right, if you follow the interface of these fingers, the reality is that the water is infiltrating at very different rates depending on where you're looking at. And particularly if you're somewhere around the tip of these fingers, the water is actually infiltrating much quicker than the rate at which the water is arriving at the top. So it's a long experiment. We can fast forward a little bit. But another fascinating thing is that these conduits, you can see once they're established, they kind of just remain there, and they become the conduits for any future arrival of water. And so there are, unfortunately, very limited field observations of this process in nature, because intrinsically, it's, you know, any structure that remains after an infiltration event will likely be destroyed if you start dug the soil out. But here are some very limited field evidence. But overall, the message here is that gravity fingering, which we see in these animal experiments, clearly provides a very efficient way for water to infiltrate through dry soil. And that rate can locally be faster than the rate of rainfall. And the standard infiltration model, which is shown on the right, does not capture this process. And so it turns out the missing physics in the standard model is the ability to describe the macroscopic role of surface tension at the infiltration front. So energetically speaking, what the model is missing is considering the fact that when water is percolating through the soil, it's also creating interfaces. So there should be an energetic penalty when you're creating interfaces. And so that aspect is missing in the original model. And so what my colleagues and I have done in, starting in the early 2000s is to try to arrive at a updated version of the standard model that can capture this type of macroscopic surface tension effects. And so we start, we're using this framework called phase field modeling framework. And basically we start by describing the free energy of the water, air, and grain, soil grain system. And so here is what the energetic equation formula look like. So you start with gravitational energy, capillary energy, and then you add this non-local energy that essentially captures the fact that you are creating interfaces as water is percolating. And so this energy formulation essentially paints a landscape over which our system will evolve over time. And so the rate at which the system evolves is what we call potential, and that's essentially the gradient of this energy landscape. And then we can complete the formulation by introducing mass conservation of water, and that the gradient flow. And then eventually we arrive at a updated model that includes the effect of surface tension at the infiltration front. So mathematically speaking, the fingered infiltration model actually bear great mathematical structure resemblance to the classic model. And the only added term, which is this fourth order gradient term, what we call, it essentially captures the role of macroscopic surface tension that energetically you're penalized for creating interfaces. And so of course, it took many years for this model to develop, but it was really, really good to see that the updated model is able to capture the fingering phenomenon. And in particular, now you can see in the simulation, just as you see in the experiments, that a significant portion of the water can travel very quickly through the gravity fingering conduits. So now with this updated model in mind, we go back to our original question, which is, how does rainfall bypass the evaporation zone? And our hypothesis is that the fluid mechanical instability of gravity fingering is somehow providing an efficient way for water to traverse through the shallow evaporation zone. And so we test our hypothesis using modeling, and as I mentioned earlier, we have now this updated model that captures the infiltration physics, and then we couple it with the standard treatment of modeling evapotranspiration, which is essentially a exponentially decay function with depth. And then we use this model we apply this model to 4 field stations along the Kalahari Transact, which is shown here. So the reason we chose the Kalahari Transact is because it's actually been the focus of a lot of eco-hydrological studies in the early 2000s as well. And especially there has been a lot of data on the rainfall patterns in these regions. And here I'm showing you 4 stations that we chose and the annual amount of rainfall that it receives. And so these 4 stations also very nicely follow a what we call precipitation gradient, meaning that the northern stations are wetter, receives more rainfall than the southern stations. And so in order to emulate the field conditions, we've delved into the literature and generated stochastic rainfall records based on the local rainfall characteristics. And so, in terms of the, this diagram that I showed you earlier, the square points are where the 4 stations fall onto. And we also generate variations of the current climate conditions by emulating either a wetter, which are these points to the right of these dashed line, and or drier scenarios, which is to the left of this dashed line. And we emulate these wetter or drier conditions by simply changing how much rain these locations receive. And so for each location, we simulate stochastic rainfall and infiltration with evaporation for 30 years. So here's an example of what happens to Tishane, which is actually one of the southern states, so it's the drier states. So on the right is the rainfall that we input into our model. And here I'm only showing you 15 years because that's all I can fit on the slides. And eventually what we're doing in the simulations is that we are collecting how much water is leaving the bottom boundary. And we deem that is the amount of water that essentially recharges the groundwater. And I forgot to mention, so the simulation domain here is about 2 meters tall by 1 meter wide. All right, so we perform these type of simulations for all the 4 sites, for all the different climate conditions. And we performed using 2 different models. One using the standard model where we capture very stable infiltration, and one using the fingered infiltration model. And as I mentioned, we simply collect how much water is being recharged by quantifying how much water is leaving the bottom as a function of time. So it goes from 0 to 30 years. And for the standard model, we plot that curve using dashed line, and for the fingered model, we use solid line. And so what we found is that under the current climate for all the 4 stations, the standard model is actually, it significantly underestimates how much water is being recharged for the southern drier states. So for example, here, the standard model, which is dashed line, predicts that 0 millimeters water will get to the aquifer, while the fingered infiltration model predicts that over the course of 30 years, you will have about 10 centimeters of water. However, for the wetter states, the northern sites, both models actually agree really well, meaning that they both predict about similar amount of water recharge. So clearly we see there's a trend in terms of how much the standard model underestimates recharge that depends on the dryness of the climate. And indeed, if we explore the rest of the parameter space where we simulate climate variations for all the stations, we also see that under a dry climate, the standard model always underestimates how much rainwater reaches the aquifer. And under a wetter climate, both models tend to agree fairly well. And so going back to our original hypothesis that we think gravity fingering somehow provides an efficient way for recharge, we think these results indirectly confirms our hypothesis. That is, with now an updated model that considers the physics of gravity fingering, the model is able to predict more groundwater recharge. So going forward, we want to also think about how is this new updated model able to help us address more quantitatively how the precipitation recharge dynamics. So what I mean by that is simply the question, when it rains in the atmosphere, does it immediately rain or only occasionally trickle deep underground? And so this question was really motivated by the recent study I mentioned earlier down in sub-Saharan Africa, where they have dug out about 30 years worth of records of groundwater table versus rainfall records, and simply ask the question of how these two correlate. And so what you see here is some graphs where the solid line here is the groundwater level and the gray bars are precipitation records. And so this is actually summarizes what our simulation shows, is that when you, in terms of how much water actually makes it into the underground environment, in a wetter climate, a larger fraction of the water makes it into the aquifer, which is probably not surprising. But what's really fascinating is we can also say a lot about the temporal correlation between rainfall and recharge. Specifically, we see that in a wetter climate, recharge tends to correlate with rainfall seasonality. And so this is shown here by example in Ganzi, where you can see that the recharge over time is a very smooth curve that increases with years. And you can see an example here in the field. However, if you're in a very dry climate, we observe that recharge is sporadic and does not correlate with seasonality. So here's an example in the field, and here's an example shown in our simulation for the drier climate for Ganzi. And lastly, when you're somewhere in between the two extremes, we do see a hybrid dynamics of sporadic and seasonal. So in conclusion, we think that gravity fingering, which is fluid dynamical instability, really helps explain how groundwater is able to reach aquifers in some of the dry regions of the world. And we think that the fact that fingering allows water to quickly traverse through the topsoil suggests a higher resilience to aridity in the future climate. And lastly, we hope that an improved model that captures this type of infiltration physics may help better quantify the precipitation and recharge dynamics observed in these drylands. So that was the end of my talk. And I want to quickly acknowledge people and departments that have really made a huge impact on my time as a Miller Fellow. So I want to first thank the EPS department. I'm really grateful for their hospitality to accommodate someone who like me, who are originally from a very different kind of PhD department. And especially, I remember the first month I was in the department, immediately all the graduate students were inviting me to go camping with them. So this is actually a picture from one of the camping trips, which are really awesome. And so people from the department, Michael, Roland, Xie, Steve Self, Steve Ring, and Tushar Jonas, and Chris, and I've all interacted a lot with them. And of course, I want to thank the Institute and all the fellows. And so here's a picture of our dumpling making party. This is way before COVID. This is actually back in early 2018, I think, 2019. So those are really great times. I can't wait to do that again soon. And lastly, I want to thank my coaches. I have 4 amazing coaches, Anna, Dan, Nayali, and Alfred. And I also want to thank my family, in particular, my husband, Ryan, and my son, Emery. So we're very lucky that we have a 4-year-old now with us. And even though it was quite a ride to give birth during the pandemic, but we're lucky that everything turned out really well, and really grateful for all the support we got from the community. And I just want to end my talk with a video I took on the right when I was reading a paper actually about gravity fingering to Emery. And there we go. And it was during one of those heat waves in August, and I had nothing better to do, but I figured I would read a paper while babysitting the same time. And it just turned out that he is one of the best listeners and a very curious learner. And I'm very grateful to have him in my life. With that, I want to thank everyone for your attention.